Hi everyone, my name is Nick from Coffee Before Arch, and in this episode of This Week in Architecture, we're going to be going over a paper that appeared in the 2019 HPCA program. So HPCA is the Conference on High Performance Computer Architecture, and we've got this paper between University of Virginia and then University of California, San Diego. And it's on Composite-ISA cores. So let's go ahead and go to the presentation that summarize this paper. All right, so let's get started. So it's full screen. All right, so Composite-ISA cores enabling multi-ISA heterogeneity using a single ISA. So let's go over an overview of the paper. So heterogeneous architectures allow applications to migrate to the core that's best, the core best for them at any given moment. So when we say heterogeneous architectures, what we mean is something along the lines of, say, ARM's big.little. So you may have a large processor core, and you may have a smaller processor core that are taped out together. And what's the implication of this? Well, you may have things that maybe you want to work in like a low power mode, and you don't want to have to be running, say, some big core in order to do some very simple tasks. So instead, you have multiple different, differently sized cores on the same chip. So in this case, we usually call that an asymmetric multi-core. So you have symmetric multi-cores that all have the same sized cores on them. Basically like if you took one core and then you just stamped it out a couple times. And then you have asymmetric multi-cores, which each of the cores has, say, a different performance. Or it can get different performance, and they're meant for different things generally. So heterogeneous ISA architectures expand on this idea. So not only maybe do you have a different core on the chip, maybe that core runs in runs a completely different instruction set architecture. So here's a core that, say, runs x86. Here's another core that runs an ARM instruction set. Here's another one that runs alpha, and it's something where there may be certain things related to the instruction set and specific instructions, or maybe the fact that you've got more complex instructions over here, which leads to a greater code density, which may be advantageous in some circumstances. But the fact that it's so complicated means that your decode logic has to be a lot more complicated. So maybe it's better to have a more simple ISA, where you trade off maybe some code density for the fact that your decode can be relatively simple. So there's a lot of trade-offs here, and in some cases, one is advantage over the other, or one has an advantage over the other. So what does this paper seek to do? It seeks to simplify the implementation, or simplify this implementation using multiple different ISAs by introducing this idea of a composite ISA. So instead of having something from ARM and something from Intel, which we'll get into in a second, which could be a little bit tricky, just use a single instruction set architecture and then partition off pieces of it to use on each of the individual cores. So let's talk about that problem and be a little more specific. So heterogeneous ISA architectures expand on asymmetric multi-cores. So not only do you have differently sized cores, you have differently sized cores that have different instruction sets being run on them. And that expands on this idea of ISA affinity. So you've got certain programs or certain types of tasks that are better within a certain ISA than they are in another. And so that's this ISA affinity. So it's naturally suited for one ISA over another. The problem is this is hard. So if you want to, say, use one of the instruction sets over another one, you can get the benefits, but then you also get all the baggage. So maybe you want maybe there's part of a certain ISA that's really beneficial for you, but you can't just take part of that instruction set. You have to take the entire instruction set. And that there may be a lot of things in there that you don't necessarily want to support, or exactly that. There may be a lot of things you don't want to support, or that's completely useless for your situation. Then we also have the legal and licensing costs. Now, if you're just dealing with one vendor, it can be a hassle sometimes, but imagine having to deal with Intel and ARM and the fact that you're using both of their IP on a single chip. It might get a little bit hairy. And then there's also this cost of core migration. So if you have different cores running different ISAs, it becomes a little tricky because all the state inside of the ARM core will be completely disjoint from all the state inside of an Intel core. So that if you needed to, say, migrate a task from one core to another, that's a non-trivial task. They're running completely different instructions. So that translation that translation of all of the code in that state that's on that one core that's, say, ARM, it's really hard to move that to another one. So a lot of tricky issues there for the potential benefit. So let's look at the parameters that we have to explore. So there's register depth, which basically says how many registers do we have or that is associated with a specific ISA. We have register width, so what are the size of the registers? Do we have 8-bit registers, 16-bit, 32-bit, 64-bit? Do we have really wide 128-bit registers? So that's what we mean by registered width. We have instruction complexity, so do we have more CISC type instructions or do we have more RISC type instructions? Predication, so this predication deals with they can be used to remove branches from your code. So predication is where we can set these things called predicates, and we make decisions based upon predicates. So you can think of them kind of like an if statement or conditional logic. And then there's also SIMD support. Do we want to support vector instructions? Is that something we want to do? And in some cases we will, in other cases not so much. So high-level design, what did they do in this actual paper? So the entire idea is to have a superset ISA. So in this case, they're specifically targeting an x86 ISA, and in their big superset ISA, they include all possible features that they can have. So not only is it full x86, but it has full SIMD support, and the multimedia extensions for SIMD and vector instruction support. And then they break it down into, okay, so does it have SIMD or does it not have SIMD? And are they complex instructions or more simple instructions? And so that's where we get this x86 plus SSE versus micro x86. And then this gets broken down into the other categories we talked about. So are they 32-bit or 64-bit registers? How many registers? And then whether they have partial or full predication. So we want to start out by picking some of these options to place out together. So remember, it's an asymmetric multi-core. So we want to pick, maybe we want a couple cores that have that use normal x86 with multimedia, with the SIMD extensions. Maybe we want some cores that have 32 bits, others that have 64 bits, and then maybe we want another core that has micro x86 that's 32-bit because we want a kind of a lower power core. So what are the main modifications versus a traditional type of architecture, or what are the main modifications that they made based upon their previous work? So their previous work in this area dealt with that idea of heterogeneous ISA architecture. So now they're going a step further. So of course they're going to need some compiler infrastructure work. You're going to need to support some new instructions there. So they use they modify the LLVM machine code infrastructure for these new encodings for instructions. Then they also have to make sure they can handle upgrades and downgrades. So upgrades are relatively simple. That generally means that you're going to a core with more features, not less. So it should support everything that the downgraded core has. And so that's generally the case. Now downgrades are a little more tricky, but turns out they're not that difficult. If we downgrade, think about the different levels that we had there. So does it support, does it have 16 registers? Does it have 32 registers? Well, if you downgrade from something that has, say, 32 registers to 16 registers, it's a pretty simple fix. Now it's going to hurt for performance, but you can always spill registers out to memory and then load them back in. So that's not too complicated. Now addressing. So we may not support as complex of an addressing mode in a downgraded core, but we can also change it to, we can do some pretty easy modification to that as well in order to, maybe if we can jump longer distances in a more complicated instruction set, we can basically tether jumps together or something in order to jump the same distance. So relatively simple fixes, unlike if we had to, say, move from an x86 core to an ARM core. So let's see what they did. So in order to get some power and area estimations, they do a full RTL synthesis of a decoder. Now, very large design space here. So we're talking about not only all of these possibilities with a Composite-ISA, but you're going to have to test these on applications. So tons and tons of simulations that they ran. So they actually used the XS EDE Comet cluster, and they ran 196,560 simulation runs. Now this is one of those things where there's always going to be more possible simulations than you could. That's even worth doing. There's no point doing a full exhaustive search on something like this. So, we don't settle for we don't get the best solution, but a lot of times we settle for the local max or the local best solution. And then there's also some things we can do to reserve, to limit the search space a little bit. So there's some obviously bad combinations that we wouldn't want to have. So let's take, for example, we would never really want full SIMD support on a core that only has 8 registers. So things like this that, just don't make any sense. We just don't even consider those architectures. So let's look at the results. So what did they actually achieve in this paper? Now, the main thing is they're trying to compare back to their previous work, which was a heterogeneous ISA architecture. So it had x86 alpha and the thumb instruction set architectures, and then plus it had hardware heterogeneity. So remember, when we're talking about hardware heterogeneity, we mean differently sized cores. So this is their target baseline they're comparing against. So their best possible, the state of the art before this paper. Then they also compare with a couple other things. So they compare it with just a normal x86 64 processor. They compare it with a single ISA heterogeneous, so x86 64 with different sized cores. Then they compare it with a Composite-ISA with fixed feature sets. So what they do is they take their ISA and then they make it look like alpha and make it look like ARM's thumb instruction set. So they don't do the same kind of Composite-ISA where they take subsets of it. They just make x86 look like them. So that's what's x86ized thumb and x86ized alpha. So instead of just completely cutting off everything, they try to just add all the features to make it look like one of those other instruction sets. And so here we have their multi-programmed workload throughput comparison. So they get the speed up on the y-axis, and then on the x-axis here, it's going to be their peak power. So at these different power budgets, what do they get? And then over here is going to be area. And all of these here are normalized to a homogeneous x86 64 processor. Now, as you can see from here, with this green bar, they do generally better than their previous heterogeneous ISA architecture. A little bit worse here. And overall, I think it's a little bit less than the original heterogeneous ISA. And then over here, the same case rings true. So for 48 millimeter squared area budget, they do better at 48, but at 64 and at 80, and then an unlimited possible area budget. On overall, they do a little bit worse, but it's important to note that they do a little bit worse, a fractional, negligible part worse. But what makes this so much more attractive is that you don't have all the complications of having to implement alpha and x86 and thumb on a single processor, legal and licensing problems, as well as the difficulties of migration. And then over here they have for this is going to be a power consumption, so EDP, energy delay product. And they see the same case kind of rings true, except this time they do better in every single case than their previous work, or the heterogeneous ISA work. And the reason for this is it's fairly intuitive. So they're able to pick the explicit features that they choose in these designs. And so when you don't have to support all of alpha and all of thumb and all of x86, when you may only want a subset of those ISAs, you can save some power because you can save a little bit of power there because you're not having to implement useless features. Okay. So it's important to note also that out of those over 100,000 runs they do here, for each of these cases they pick the run or the Composite-ISA, the individual case of the Composite-ISA that worked best for each of these situations. So the combination that worked best for 20 may not be the same one that worked best for 40, so on. Now for the results section over here, this is going to be for single thread performance. So what we still care a lot about single thread performance. It's important that we don't just pretend everything is parallelizable or embarrassingly parallel. So over here, what we see is that as far as peak power goes, at these different power budgets, so here this is going to be speed up for performance. So again, very similar comparison between the previous heterogeneous ISA and the Composite-ISA. That's the green bar. It's also neat to note that if you just take a single instruction set and you make it look like these other instruction sets, you can still do a pretty good job at getting to this this improvement over here of about a little more than 10% or so overall. And then again, the same thing as far as peak power goes. So in this case, lower is better. So they do a little bit worse than the heterogeneous ISA architecture, but not by much. Overall, it's still comparable. And remember, we can't just take, just because it performed worse here, throw it out. There's a lot of things that make this a lot more attractive as a solution. And then we see the same thing over here. So again, down here, we've got single thread performance and EDP under an area budget this time instead of a power budget. And again, so outperforms at 48 millimeters squared, underperforms compared to heterogeneous at 64 and 80, and then on average, a little bit worse. And then the same thing happens with area budgets as well. Better at 48, worse at 64, 80, and the unlimited area budget. So what else did we get from this paper? So there's specific areas where downgrades really kill performance. And this is namely going to be a downgrade to 8 registers. And this is fairly intuitive. Things will be compiled specifically to use, 16, 32 registers. So if you downgrade to 8, you're going to be nothing but spilling them out to memory and having to fill them back in. Another interesting thing to note is that generally all ISA features are typically included in the total design. So we've got this really great diversity that turns out for the best performing architectures tended to have some with SIMD, some without, some with full predication, maybe some without, but they included the best ones typically included all of the features. So you'd at least have one core with full predication, another with full SIMD support, one with the full 64-bit registers, and with, say, 32 registers as your register depth. It's also important to note that, so what does this also imply? It means that you get some big wins here when it comes to migrating cores. And that's mainly because cores are not going to have completely disjoint features. So you may move from one core to another that has a different number of registers. Maybe it still has the same SIMD support though. So you're not going to lose it. You're going to lose some performance on spills and fills from registers, but you didn't get rid of your SIMD support. So the other thing is overhead from downgrades are minimal. So yeah, that's what we just talked about, thanks to the feature diversity. And it's usually as good or better than heterogeneous ISA implementation with a much easier implementation. And over here, we've got workload throughput with downgrade cost, and we see that the Composite-ISA and the Composite-ISA with migration cost, just about the same. They're almost identical. So what's the conclusion for this paper? So you get the advantages of a heterogeneous ISA architecture without licensing, implementation struggle. It's far better than single ISA designs, and it's as good or better than the heterogeneous ISA designs. And they see a 19% performance improvement overall and a 30% energy savings versus that homogeneous ISA design. So a couple things to think about, though, in this paper is that it's not... it sounds like when I say some of these things that, everything here, we should be implementing this today. But there still are a lot of challenges. So when it comes to migration cost, when I was reading the paper, it was still a little bit unclear as far as what that is realistically. In the paper, they reduce some of their migration costs, and they don't simulate every possible scenario where migration could be actually really, really bad. So in reality, migration might be a lot worse than it's made out to be in this paper. So it's important to know that. And then once you actually get to implementing something like this, there could be some other things that crop up in terms of, maybe it's part of migration, maybe it's part of overall design complexity of having all of these different ISAs when it comes to the decode logic. Maybe there's some stuff there that would be interesting to look at more. But overall, it shows that it's at least a step in a direction of, okay, if we have heterogeneous architectures, they see improvement over homogeneous sometimes. If we add heterogeneous instruction sets, we see more improvement, and then we can, take back some of that complexity or make it a little more simple by having this superset ISA that they can just slice off regions of, and it simplifies a lot of it. And that's what they call this composite ISA. So that's going to do it for this paper overview. If we go ahead and go to the GitHub page that I have for Coffee Before Arch, we've got all the stuff that we work on here. And if we go to This Week in Architecture, we've got the previous video, where we went over one of the ASPLOS 2019 papers that was on quality of service system. We'll have a link to this video. We'll have a link to the paper here from HPCA 2019. And that's going to do it for today. So I'm Nick from Coffee Before Arch, and I hope you have a nice day.